In the previous section, we learned how enthalpy of vaporization and enthalpy of fusion were directly proportional with intermolecular forces. In this section, we're going to focus on how to actually do some mathematical calculations involving enthalpy of vaporization and enthalpy of fusion. So in this case, we're going to work with the enthalpy of vaporization. Remember, this is the amount of energy required in kilojoules per mole to separate, in this case, the acetone molecules from one another. So there will be no temperature change when we add this heat energy. When we add this heat energy, the heat energy is being used to take molecules in the liquid phase, which are relatively close to each other, and of course they have intermolecular forces, in the case of acetone, dipole forces, that attract the molecules together, and to separate them into the gas phase, where they're essentially a much greater distance between them. And in order to do that, we have to add energy to overcome those forces of attraction, which is why enthalpy of vaporization is directly proportional with intermolecular forces. So it says, how much energy does it take to boil 8.9 grams of acetone at its boiling point? And what that essentially means is, how much energy does it take to turn it from a liquid to a gas at its boiling point? So no change in temperature. So let's look at this. Well, one way we could look at this is, in order to find the heat energy required, is we could do Q equals N, the moles, times the enthalpy of vaporization. So if you like it as a formula, you can convert grams to moles, we have molar mass, and then plug it into this formula. Of course, with many formulas, you can also use dimensional analysis, and this is no exception. And that's how I'm going to do this. But in the next question, I'm going to use this. So it doesn't really matter how you do this. So here, what I'm going to do by way of a plan of attack is I'm going to convert from grams of acetone, which I'm going to abbreviate ACE, to moles of acetone, and then to kilojoules required to convert those molecules from the liquid to the gas. So starting with 18.9 grams of acetone, I want to convert it to moles, so I'm going to use the molar mass, which is given. I want to put the 58.08 grams of acetone on the bottom and the 1 mole of acetone on the top. Now I want to convert it to kilojoules. So in this case, this is kilojoules per mole, kilojoules per 1 mole. I want moles to cancel out, so I put the 1 mole of acetone on the bottom and the 31.3 kilojoules on the top, like so. And when I do that math and I round to 3 significant figures, I find that it requires 10.2 kilojoules of heat energy to separate these acetone molecules with no change in temperature. So in the next example, what we're going to look at is what is called a phase change diagram. And in the next section, we're going to look at a phase diagram. So it's important to know the difference between a phase change diagram and a phase diagram. So this is a more complex example of what we just talked about. So here it says, how much energy does it take to heat 47.2 grams of water from minus 18 degrees C to 112 degrees C? And because this is water and because we're familiar with water, we know that we go through 2 phase changes when we do this. Specifically, at minus 18 degrees C, ice is what is present. We heat that to 0, then it's going to melt, so we need to consider the enthalpy of fusion. And then it'll be a liquid. We're going to heat it from 0 degrees C as a liquid to 100 degrees C as a liquid. Then it's going to boil, and then it'll be a gas. So at the end, we'll have steam that we have to heat from 100 to 112 degrees C. Now, in order to make our lives a little bit easier here, I'm going to be honest with you, this is a particularly annoying type of problem. But to make our lives a little bit easier, it can be easier to visualize this in terms of a graph, okay? And this graph is the phase change diagram that I was mentioning before. So we're going to have 2 axes on our graph. We're going to have heat, or heat added, which will just be in this direction. And we're going to have temperature, in this case in degrees C on this axis. Now we want to write our 2 milestones. So we'll start way down here at minus 18 degrees C. And we'll go all the way up to here to 112, I think. Yeah, 112 degrees C. And then we want to put 2 more milestones on our temperature axis. Okay, the first one is 0 degrees C, and the last one is 100 degrees C. And the reason these 2 milestones are important is because we need to have phase changes occurring at these temperatures, right? The melting point and boiling point of water are 0 and 100. I on purpose chose water for this example so that we didn't need to, remember what the melting and boiling point are or think about that. We can basically just do that from memory because we're familiar with water. So starting at minus 18 degrees C, we have ice. We add heat. What happens to the temperature as we add heat? Well, what happens to the temperature is the temperature increases, but it doesn't increase forever. It comes to a point where it stops increasing. Okay? So this is basically what we have. We then reach 0 degrees C ice, and we add heat, but the temperature doesn't change. What is occurring here is a phase change. We're going from solid water to liquid water. Okay, I draw my L like that so it doesn't look like a 1. So we're going from solid to liquid water. Said another way, fusion is occurring here, and we need to consider the enthalpy of fusion here. We then have liquid water at 0 degrees C. We add heat, the temperature increases, like so. Okay. Then at 100 degrees C, we have liquid water. We add heat, but no temperature change, so we get a flat line again, and we convert it into a gas. I will mention that this is not proportional. Okay, if this were proportional, I'd have to come like over here. So basically, this is not proportional to what it'll actually be, but you get the idea that we add heat and it becomes a gas. What are we doing here? We are separating the molecules, we're boiling it. This is where the enthalpy of vaporization comes into play. Then finally, we have gas at 100 degrees C. We heat it to 112 degrees Celsius, the final temperature, because that's what it asks about. And what we end up with here is essentially 1, 2, 3, 4, 5 segments. And you may be asking yourself, if you're familiar with this, can I consider 1, 3, and 5 the same? Turns out you can't, okay? Because unfortunately, the amount of energy required to heat up a specific mass of ice is different for liquid water is different than steam. So unfortunately, you have to consider this as 5 unique segments, which I mentioned at the beginning. This is a tedious problem, and that's the main reason why. Okay, so let's take a look at this. We know how to express segment 2, all right, because we just talked about it. Q, the amount of heat, equals N times, in this case, the enthalpy of fusion, because here we're going from solid to liquid. And in segment 4, Q equals N, the number of moles, times the enthalpy of vaporization, just like we did in the previous problem, because here we're going from liquid to gas, which is what we were doing in the previous problem. Believe it or not, you actually know the formula, and it's the same formula, for segments 1, 3, and 5, the sloped parts where the temperature is changing. And that is Q equals M, the mass of the water in grams, times the specific heat capacity times the change in temperature. Okay, so this is something we already did in a previous chapter. So basically, you are familiar with this equation. So this is how we're going to find Q for segments 1, 3, and 5. Okay, and these are how we're going to find Q for segments 2 and 4. So before we do that, we need to do a couple of things. The first thing we need to do is we need to be familiar with the specific heat capacities. And as I mentioned a second ago, it's different for each phase. So the C sub S of ice is 2.09 joules per gram degrees C. And these would be provided to you in the homework or on a test. You don't have to memorize these, okay? The C sub S of water, liquid water, is equal to 4.18 joules per gram degree C, and you may remember that one from when we talked about that in the previous chapter. And the C sub S for steam or gaseous water is equal to 2.01 joules per gram degree C. And I mentioned that this is one of the things that really makes this problem tedious, so I can't consider the total temperature change and calculate segments 1, 3, and 5 all at the same time because they each have a different C sub S, so therefore I have to do this individual times. Another annoying thing is, in the case of here, I have the mass times the specific heat capacity times the change in temperature. In the case of these two equations, I have moles. So in some equations I have to put in masses, in some equations I have to put in moles. That's a little bit tedious as well. But what I found over the years is it makes our life a little bit easier if we go ahead and convert this 47.2 grams to moles right off the bat, and then we can use those moles when we need them. So starting with 47.2 grams of water times 1 mole of water per 18.02 grams of water, we find that in this case we have 2.62 moles of water. So now that I have my specific heat capacities, I have my mass, I have my moles, I am good to go to try to do this, but I still have to do this one step at a time. So the first thing I want to do is segment 1, just because it comes first. All right, and segment 1 involves going from minus 18 degrees C solid to 0 degrees C solid. So I'm going to write that as minus 18, all right, degrees C solid to 0 degrees C solid. So that's what I'm going to write it. In order to do this, because there is a change in temperature, right? We went from minus 18 to 0. I'm going to use the equation that has change in temperature. Notice this equation has change in temperature and this one doesn't. But basically for the sloped ones that don't have a flat slope, we're going to use this equation here. So Q equals M C sub S delta T. Plugging in, the mass is 47.2 grams times specific heat capacity, which is for ice, 2.09 joules per gram degree C, times the temperature change, which is 18 degrees C. Okay, and when we do that, we get 1,800 joules, but we're going to need it in kilojoules, so I'm just going to divide by 1,000, 1.8 kilojoules. All right, so it takes 1.8 kilojoules of heat energy to raise the temperature of 47.2 grams of ice from minus 18 to 0. Segment 2. In segment 2, we are not changing temperature. We're going from solid ice to liquid water. All right, so specifically, we're going from 0, let me rewrite that, 0 degrees C solid to 0 degrees C liquid. All right, and to do that, we're going to use Q equals N times delta H of fusion. And remember, fusion is the chemistry word for melting. So this is basically what we're going to do in segment 2. Note, we have no temperature change, so we can't use the equation with delta T. So if you're not sure, if you're stuck and you're not sure which equation to use, don't use the one with delta T if there is no delta T. So when we plug these in, moles, we figured that out to make our lives a little easier here, 2.62 moles times the enthalpy of fusion of water, as we talked about before, is 6.01 kilojoules per mole. Again, you wouldn't have to memorize that. I didn't put it here on the problem because I knew I was going to be going over it with you, but you wouldn't need to memorize that. That would be provided to you. And when you do that, you find that Q is going to be equal to 15.7 kilojoules. All right, so segment 2, we get 15.7 kilojoules. Let's look at the next one, segment 3. Segment 3, what are we doing? We're going from liquid at 0 to liquid at 100. So we have 0 degrees C, liquid, to 100 degrees C, liquid. All right, all the temperatures where water is a liquid. In order to do this, we need to use this equation again. Again, we don't have the flat slope. We have the slope, if you will, okay? Or there is a temperature change, however you want to think about it. So we're going to go back to the other equation. Q equals m C sub s delta T. In this case, the mass is the same, 47.2 grams. The C sub s is not the same, okay, for water. It's 4.18 joules per gram degree C when it's liquid. And then the change in temperature is 0 to 100, which is 100 degrees C. And when we do that, we find that it is going to be 19,700 joules, or 19.7 kilojoules of heat energy to heat this water from 0 to 100. All right, segment 4. What are we doing in segment 4? Well, in segment 4, we're going from 100 degrees C liquid to 100 degrees C gas. So we're boiling the water at its boiling point. There's no temperature change. We're just converting from a liquid to a gas, which again, this energy is to separate those molecules as we discussed in the previous section. So when we take a look at this, we want to use this equation, Q equals N delta H of vaporization. We already found the moles. All right, so we have that. So 2.62 moles times the enthalpy of vaporization, which is going to be 40.7 kilojoules per mole. Again, I wouldn't expect you to know this off the top of your head, but we had just talked about it in the previous section, so that's why I didn't put it on the sheet. And when you do that, you get 107 kilojoules. Something interesting to point out. If I add up 1.8 kilojoules, 15.7 kilojoules, and 19.7 kilojoules, they're far less than 107 kilojoules. Said another way, it takes more energy to vaporize the water, okay, than it does to heat the water from -18 to 100 degrees as a liquid. So it takes a lot more energy to vaporize it. You may have heard that steam burns people more than boiling water. Well, now you know why. It has a heck of a lot more energy in it, okay, in this case 107 kilojoules more energy in these 47.2 grams, okay, even though it's at the exact same temperature. Let's look at segment 5, the last segment. So 5, we're going from 100 degrees C as a gas to 112 degrees C as a gas. Okay, so we're back to Q equals M C sub S delta T. And when we plug in the numbers here, the mass that we have is 47.2 grams. The specific heat capacity of steam is 2.01 joules per gram degree C. And the temperature change here from 100 to 112 is 12 degrees C. When we do that, we find that Q equals 1100 joules, or 1.1 kilojoules. So for each segment, we found the amount of energy required. How are we going to find the energy to do this whole thing, to go from -18 to 112? Well, we're simply going to add them together. So we take our 1.8 kilojoules plus our 15.7 kilojoules plus our 19.7 kilojoules plus our 107 kilojoules plus our 1.1 kilojoules. And because I've run out of space, I'm going to write it above. When we add those all together, we get 145, that should be a 5, kilojoules. All right, so this is the total amount of energy it requires to heat the water from 47.2 grams of water from -18 to 112. the phase change diagram is very helpful for visualizing what is going on. And in the actual lecture notes, as you can probably see, okay, it looks a little better than my poorly written one here. But this gives us an idea of where the energy is going when we are incorporating phase changes. So we add energy and the temperature doesn't change. Remember, enthalpy of fusion and enthalpy of vaporization are directly proportional with intermolecular forces.